Greetings, everybody. Learning as a hobby here. I'm going to finish up chapter 4 in Spivak in this video. If you saw my last video, I did the summary of Appendix 3 for chapter 4. And in this video, I'll finish up the exercise set for Appendix 3 and chapter 4. Not the entire thing. I think there was like 10 or 13 questions or something in the exercise set, but a lot of them are just wrote like graph this polar curve or whatever. So I skipped over those and just did the ones that I found interesting. So let's get right to it and finish up this chapter. All right, so let me bring up my solutions. I started with question number 1, so let me just read that out and I'll show you my solution. Okay, so question 1 says, if 2 points have polar coordinates r1 theta 1 and r2 theta 2, show that the distance d between them is given by that formula, d squared equals r1 squared plus r2 squared minus 2r1 cosine, minus 2r1 r2 cosine theta 1 minus theta 2. And he wants us to say, what does this mean geometrically? So what I did was just use the distance formula for 2 points in Cartesian coordinates. So if r1 theta 1 has Cartesian coordinates x1 y1 and r2 theta 2 have Cartesian coordinates x2 y2, then the distance formula says that the square of the distance between those 2 points in Cartesian coordinates is x1 minus x2 all squared plus y1 minus r2 all squared. Y1 minus y2 all squared. And then just plug in the polar representations for those for x1, x2, y1, and y2. So you get this expression here, this one here, and then multiply everything out. And once you do that, just use a couple of trig identities. Remember that cosine squared plus sine squared is always 1 by the Pythagorean identity. So this is 1, this is 1, and cosine theta 1 times cosine theta 2 plus sine theta 1 sine theta 2 is equal to cosine theta 1 minus theta 2 by the difference formula for cosine. So we end up, when we simplify everything, with the formula that he wanted us to show, right? And essentially the geometry behind this is it's just the law of cosines. So if you look at the triangle that you can build here, this is r1 theta 1, r2 theta 2. The red line is the line segment connecting the two. So the length of that line segment, that red line segment, is the distance d. But notice we get this triangle here. This angle is theta 1 minus theta 2. So that's this one here. The opposite side to that angle is the red line segment. The green side r1, the blue side r2 are the other sides of the triangle. So if you find the square of the length of d using the law of cosines, notice you get exactly the same thing. So it's just a statement of the law of cosines. Okay, that's question number 1. Next one I did was question number 5. Consider a hyperbola where the difference of the distance between the 2 foci is the constant 2a, and choose one focus at the pole or the origin if you like, and the other at the point with Cartesian coordinates negative 2 epsilon a comma 0. In this case, we must have epsilon greater than 1. You'll see why when I draw the picture down below. Show that we obtain the exact same equation in polar coordinates r equals lambda over 1 plus epsilon cosine theta as we derived for an ellipse. Right. So here's the picture. I just drew a general hyperbola with one of the foci at the pole or at the origin, if you like. This is the polar radius here. This is our pole. And this is our other focus here, right? So these points have coordinates. The foci have coordinates 0, 0 and negative 2 epsilon a comma 0. And the point P here has coordinates x, y. It's a point on the hyperbola. Okay, and by the definition of the hyperbola, we know that the length here plus the length here has to be the constant 2a. Right, and then we can find formulas for those distances using the distance formula. R squared is x squared plus y squared, and r minus 2a squared is equal to x minus, in parentheses, minus 2 epsilon a all squared. There should be an extra parentheses here. Plus y squared. right? We know that this distance here, by the way, is r minus 2a because of this fact here. So just scroll down. All right, and then just squaring both sides, simplifying both sides, you get the next equation that I have here. I just expanded everything and combine like terms. And if you subtract the equation r squared equals x squared plus y squared from the other equation, you end up with this one over here. And if you divide out by 4a, you get this equation, which is the exact equation that we got in the chapter when we were deriving the polar form of the equation of an ellipse. So we get this formula here that he wanted us to show. The only difference here between this one and the one in the chapter, in the appendix itself, is that in this case epsilon is greater than 1 rather than less than 1, and that's because, actually I don't remember if I showed this in the picture, but that's because the distance, let me use a different color so it shows up better here. Use blue. So the distance here is bigger than the distance between the vertices of the two branches of the hyperbola. So that's why epsilon's greater than 1. All right. That's question number 5, I think it was. Question number 6. Consider the set of points xy such that the distance xy to 0, to the origin, is equal to the distance from xy to the line y equals a. So see the figure. So I actually have it drawn. This is the picture that he drew in the book without the green lines there. I put those in myself. You have a vertical line y equals a, and if you look at a point that lies on the curve that we're looking at here, which we're assuming is a parabola, in other words, we want to show that the distance to the if we assume that the distance r is equal to the distance d that I have drawn in the picture here, then we get a parabola. Sorry, did I say hyperbola? We get a parabola. So, and sorry, I'm losing my point here. Let me go back to the question. Consider the set of points such that the distance xy to 0 is equal to the distance from xy to the line y equals a. See the figure, so that's what I showed. Show that the distance to the line is a minus r cosine theta, and conclude that the equation can be written a equals r times 1 plus cosine theta. Notice that this equation for a parabola is again the same form, r equals lambda over 1 plus epsilon cosine theta. So just again, using the distance formula, it's relatively straightforward. So we know that r squared is x squared plus y squared. Again, the distance d squared is x minus a all squared plus y minus y squared, which is the same thing as a minus x squared. Take the square root of both sides, and you see d is equal to a minus x. And then just replacing x with r cosine theta, you get the formula that he wants there. And then assuming that r and d are the same, have the same value, the lengths are the same, then 0 is equal to r minus d, which is equal to r minus a plus r cosine theta, which if you rearrange and factor out the r is equal to r times 1 plus cosine theta, and then minus a, and then just bring the a to the other side and you get the form that he asked us to find. So that's the problem. All right, that's question 6. Question 7. Now for any lambda and epsilon, consider the graph and polar coordinates of the equation r equals lambda over 1 plus epsilon cosine theta, which implies that r is equal to lambda minus epsilon x for lambda equal 1 minus epsilon squared times a. Show that the points satisfying this equation satisfy 1 minus epsilon squared x squared plus y squared equals lambda squared minus 2 lambda epsilon x. And then he says using problem 416, which is one of the problems I don't think I did in the video for the exercise set for chapter 4, but what that does, what he talks about in 416 is just, he talks about the general form for the equation of a conic section, which I'll write here in case you don't remember that. So this is the general form of the equation of a conic section, and depending on the values of the coefficients, you get either an ellipse or a hyperbola or a parabola or two 2 lines or 1 line, or you get nothing. So those are the possibilities. So he wants us to use that fact to show that this is an ellipse if epsilon is less than 0. Sorry, it's less than 1. A parabola if epsilon is equal to 1, and a hyperbola if epsilon is greater than 1. All right, so we'll do that down below. Okay, so assuming that r is given by the equation, he said 1 minus epsilon squared times a plus epsilon x, then x squared plus y squared, which is equal to r squared, is equal to the square of the right hand side above. So you get 1 minus epsilon squared times a squared plus 2a, 1 minus epsilon squared epsilon x plus epsilon squared x squared. And just using the definition of lambda, that's equal to x squared plus y squared equals lambda squared plus 2 lambda epsilon x plus epsilon squared x squared, and then bring the epsilon squared x squared to the left hand side and factor out the x squared, and you get the equation that he wanted us to derive. Okay, so that's the first part. Then if epsilon is less than 1, then 1 minus epsilon squared is positive, so you get the equation of an ellipse. If epsilon right, because you get if this is positive, right, then you get a sum of positive terms here equals this expression, and from the general equation of a conic section, that gives you an ellipse. And then case 2, if epsilon is equal to 1, then the equation simplifies to y squared equals lambda squared plus 2 lambda epsilon x, which of course is the equation of a parabola, which you should remember from algebra, pre-calculus, whatever, whenever we took it. Again, that follows from 416. It follows from the general form of the equation of a conic section. And then lastly, case 3, if epsilon is greater than 0, then 1 minus epsilon squared is less than 0, and that gives you a hyperbola, again, by 416. So that's the answer for this one. Next one is question number 8. There's 3 parts to it. First 2 are relatively straightforward. He just wants us to graph those 2 cardioids and show that they're the same graph. So first, he wants us to sketch the graph of the cardioid r equals 1 minus sine theta, which I did down here. And if you remember from the appendix summary that I did, I explained how I like to graph polar curves. I first like to graph the equation in rectangular coordinates first, and then I use that to figure out what the polar graph looks like. So that's what I did here. Something to note is that the graph starts and ends here for this equation, if you start at 0. For part B, he also wants to graph us to graph the cardioid, but the equation in this case is r equals minus 1 minus sine theta. So again, I did that down here. So first I graphed the equation in the rectangular sense first, and then I used that to get the polar graph. And if you look, the 2 graphs are exactly the same. Well, my drawing isn't the same, but if you drew them correctly, if you drew them more accurately, that would be exactly the same. But the only difference is that the graph starts and ends here instead of starting and ending over here. That's the only difference. Just an aside, these graphs are called cardioids, if you notice, because they look like hearts when you draw them. All right, so that's A and B. Part C says show that it can be described by the equation x squared plus y squared equals square root x squared plus y squared minus y, and conclude that it can be described by the equation x squared plus y all squared equals x squared plus y squared. So all we have to do is just plug in the formulas for going back and forth between polar and Cartesian coordinates. So for example, if you start with r equals 1 minus sine theta and multiply through by r, you get the equivalent equation, r squared equals r minus r sine theta. And then using the formulas, r squared, remember, is equal to x squared plus y squared. And r itself is equal to square root of x squared plus y squared. And r sine theta is equal to y. So you get the form that we want. And then all you have to do is bring y to the left-hand side, square both sides, and we get the form that we want. Right? So this is the Cartesian equation for the cardioid. Okay. And last one that I did, question number 10, there's a bunch of parts to this, so let's take them one at a time. Part A is, again, relatively straightforward because it involves just graphing out a polar graph. So in part A, he says sketch the graph of the lemniscate, r squared equals 2a squared cosine 2 theta, which I did down here, again, using the method that I described before. So I like to graph the equation in rectangular coordinates first, and then I use that to get the graph of the polar curve. And here the lemniscate, if you notice, looks like the infinity symbol. And I believe, if I remember correctly, the shape of the lemniscate is the basis for the symbol that we use for infinity. So it kind of looks like the infinity sign when you graph it. All right, that's the lemniscate. Part A. Part B, find an equation for its Cartesian coordinates. So again, relatively straightforward. You just use the formulas for going back and forth between polar and Cartesian coordinates. So here, if r squared is equal to 2a squared cosine 2 theta, I can write down using an identity for cosine 2 theta. If you remember, cosine 2 theta is the same thing as cosine squared theta minus sine squared theta. And then I can multiply through by r squared. So you get r to the fourth on the left-hand side equals 2a squared in parentheses r squared cosine squared theta minus r squared sine squared theta. And then r to the fourth, which is r squared squared, right, is equal to x squared plus y squared squared equals on the right-hand side 2a squared. If you remember, r cosine theta is x, so r squared cosine squared theta is x squared, and r squared sine squared theta is y squared. And that gives you the Cartesian equation for the lemniscate. Okay, so that's part B. Part C says show that it is the collection of all points P in the figure satisfying D1, D2 equals a squared. So this is the figure he's referring to. So D1 is the distance from this point to the point P that lies on the curve, and D2 is the distance from this point to P, which again, P lies on the curve. And we want to show that if the product of those two lengths is equal to the constant a squared, then we get a lemniscate. So let's actually show that down. Let's see, where did I do that? Over here. Okay, so the length d1 squared is by the distance formula, x plus a all squared plus y squared. And again, by the distance formula, d2 squared is x minus a squared plus y squared. And if we assume that d1 times d2 is equal to a squared, then that means a to the 4 is d1 squared times d2 squared, which by the formulas that we just derived a second ago, is equal to x plus a squared plus y squared times x minus a squared plus y squared. And then just simplifying everything and combining like terms, etc., you get this equation here. This is equal to a to the 4, by the way. And then if you subtract these things from both sides, you end up with this equation here, which, if you notice, is the Cartesian equation for the lemniscate that we derived in the previous part. All right, so that shows that that geometric condition gives you the lemniscate. Okay, that's part C. There's one more part to this question. Make a guess about the shape of the curves formed by the set of all P satisfying D1, D2 equals B when B is greater than a squared and when B is less than a squared. So just going down here for part D. I didn't mark this. This is the start of part D here. I guess I didn't write that down, but let me do that so it's not confusing. This is the start of part D. So using that fact that B is equal to D1 times D1 times D2 is equal to B, you get a similar equation to the one that we got in part B, I think it was, but you end up with this extra constant. So here I'm just deriving that. You end up with this extra constant here. So you get r squared is equal to 2a squared cosine 2 theta plus in parentheses b squared minus a to the 4th. Right, and if b is less than a squared, the curve gives you another lemniscate contained completely inside the other one. And if B is greater than A squared, then the curve is a larger lemniscate containing the others. Let me just show you on Desmos so you can see what I'm talking about. If I can, let me see if I can share my screen with Desmos. Okay, so here, just get rid of these for a second. The red curve here is the lemniscate with the equation that we had, 2a squared cosine 2 theta, where a is 1. So I chose a equal to 1. So then if you graph that, again, you get the lemniscate that I have here. That's for the specific value a equals 1. For the constant b squared minus a squared equaling something negative, that's the same as the condition b less than a squared. You get a curve that looks like this. So you can, if you adjust the constant here, you can see how the curve changes. Actually, let me just move this up over here for a second, so I can adjust the constant here. So for example, if you make it bigger, let's say 1.5, notice the lemniscate gets even smaller. Make it 1.8. Again, it gets even smaller. You can't make it bigger than or equal to 2, though. Notice that it doesn't even give you a curve, and that's because for all values of theta, 2 cosine 2 theta minus something bigger than or equal to 2 will either give you 0 or will give you a negative number. So the curve doesn't exist for those values. But if you make it small, let's say 0.01, notice that the curve gets closer and closer to the red curve. So if I make it 0.1, or maybe I make it 0.01, notice it gets really close to the red curve there. Okay, and similarly, if b is greater than a squared, you get a curve that completely contains the other one. Oh, sorry, lemniscate, which completely contains the other one. So here, notice the constant I have here is +1. If you make it bigger, so 2, again, you get a bigger curve. 3, you get something that looks like this, and so on and so on. For those values, that for a value like 3, notice that actually this is not a lemniscate. It contains the lemniscate, but the value 2 cosine 2 theta plus 3 is never 0, so it doesn't curve back down to the pole. So for values bigger than the constant bigger than 2, you'll get something that it's no longer a lemniscate, but it contains it, if that makes sense. And again, if you make it small, constant small, notice that it gets very close to the red curve. So that's how the curves change. Okay, and that's it. That's basically question 10. Parts of question 10. Let me just stop my screen share for a second. All right, guys. So we're finally done with chapter 4 in Spivak. It took us long enough. It took me long enough, I guess, right? You guys didn't have anything to do with it, but hopefully you were following along though. And some of the problems in this chapter were pretty fun. But I think it took me so long. I just kept putting it off because it was such a long chapter. But we're done with it now, and we'll move on in the next video. Let me just give you really quick before I end this one an idea of what's coming up. So we still have one section to do to finish chapter 1 in the Simmons book. I have 2 sections to finish in the Schifrin book. But before I do those 2, I want to actually go on and finish chapter 2 in Taylor. And the reason for that is the last section we did in Simmons, that material applies to the material, in chapter 2 in Taylor. So I want to actually do that chapter first. And then we'll come back around and we'll finish Schifrin chapter 1 and Simmons chapter 1. Then we can go back to Axler, and then we'll come back around and start on chapter 5 in Spivak, which is the beginning of the calculus material in the book. So that's going to be exciting. I hope you guys enjoyed this video and all the other ones that I've posted so far. If you like this content, please do like and subscribe to videos. It helps the channel. And keep an eye out for Taylor Chapter 2 that's coming up soon, maybe this weekend even, or at least parts of it. So I'll see you guys in the next video. Until that time, keep learning. And if you have any comments or questions or anything, just let me know in the comment section, and I'll see you guys in the next one.